Hey guys, and welcome back to another video from the Waste Tutor. In this video we're going to be dealing with the third video or unit of the functions, the broad general functions topic that I've defined as the functions topic, and that is on powers and polynomials. Now we've already dealt, actually, as we'll see, with two types of polynomials, those being linear and quadratic polynomials, but now we're going to be extending that to higher degree polynomials. So let's get straight into it. With the unit overview. So in the first section of this video, I'm going to define what a polynomial is and show you how you can identify the degree of a polynomial. I'll also consider n equals -1 and n equals 1/2 as examples that aren't polynomials, but it is grouped within the powers and polynomials section, and you do need to know what those graphs look like. And I think you go into that with a bit more detail in inverse proportion as a section as well. Then we will go on to expanding and factorizing polynomials. We've already looked at quadratic polynomials, so we'll revisit that, factorizing quadratics, and we'll also look at factorizing cubics. Beyond that, there's not as much of an emphasis on being able to factorize or expand, but those are questions that could come up, and so I'll show you some techniques like factorizing by inspection and algebraic long division to factorize more complex polynomials. And then I'll be looking at being able to factorize it given graphic representation, so being able to factorize a cubic given a graphic representation of the cubic, and then also being able to solve cubic equations for specific values of x or y given a equation. I won't be able to go over anything with the class pad. Maybe that's something I upload in the supplementary content, or we'll see how that goes. But for now, those are all of the points I'll be covering. Okay, so the first thing I want to do is I want to define what a polynomial is. Now, what a polynomial is it's a collection of x terms which have powers that are positive integers. So we have an xa maybe, or let's say we'll label the coefficients of these x terms with the Greek alphabet. So I'll just do alpha xa plus beta xb plus gamma xc plus etc. etc. And here, a, b, and c are positive integers. And so this is what a polynomial is defined as. Now, another important property of a polynomial is its degree. That is, the degree being the highest power of x that exists in that polynomial. The examples of polynomials we've dealt with are linear polynomials like y equals 2x plus 1, for example. And in this case, the highest power of x is a x to the 1. So a linear polynomial is of degree 1. And similarly, we've had a look at quadratics. We've had a look at, for example, x squared plus 2x plus 1. And here, you know that's the same function as this. But we also have this x squared, and this is of degree 2. And so even though we have an x of degree 1, the x of degree 2, x squared, which is of degree 2, supersedes that. And so quadratics are known to be of degree 2. And in this video, we're going to be going over higher degrees, for example, x cubed, x to the 4, which are referred to as quartics. These are cubics. We have quartics, and we can have quintics. And you can go up as high as you want. You can go x to the 6, x to the 7, etc., etc. Okay? And so you have multiple different polynomials here, multiple different degrees. And we're going to be looking at factorizing some of these, expanding them, and we have a particular focus on cubics as well, rather than quartics and quintics, for example. Just in terms of identifying coefficients and degrees of polynomials, we
we have, in this case here, this alpha, this beta, and this gamma are all coefficients. And more specifically, alpha is the coefficient of the x to the a. Beta is said to be the coefficient of x to the b. Gamma is said to be the coefficient of x to the c, and then so on and so forth for the rest of the terms that are contained within these ellipses. Okay. Now, an important thing I defined in my definition of the polynomial is that all the powers of x are positive integers. And so as a result, if we have, for example, a polynomial where we have x plus x to the 1/2, for example, that would not be classified a polynomial. And that is owing to the fact that we have a non-integer power here. And similarly, if we have x squared plus x to the -1, this would also not be considered a polynomial, owing to the fact that this is a negative integer. Okay? But nonetheless, we're going to have a look at the properties of x to the -1 and x to the 1/2, because these are two examples that are included on the syllabus within this section for some reason. So that's just the order I'm going to go. That's just the order I'm going to follow here. So the first example I have that they go over is they go over x to the -1. So we have a graph of y equals x to the -1. Now, as we'll see in index laws, and this might be something you've covered already, a negative index will cause it to be the reciprocal function. So we will have 1 over x is x to the -1. That is 1 over x to the 1. So we have 1 over x is x to the -1. And so if we look at our graph of this, and we're considering how it might look, we see that this is said to have a hyperbolic shape. It's a hyperbola, and it looks kind of like this. And if we observe the properties of x and substitute different values of x into y equals 1 over x, then we can see why this is the case. For example, we can see here that we have something called an asymptote. That is, there exists no y value for which x equals 0. Okay? And so the reason why that's the case is because when x equals 0, we have a case of 1 divided by 0, which is by definition undefined. Okay? And if we consider x tending towards positive infinity, if we have y equals 1 over x and we have x tends towards positive infinity, then what happens is we have y equals 1 over positive infinity. And so as a result, y starts tending towards 0. And importantly, it starts tending towards 0 because we have 1 divided by a really, really, really big positive number. And if we have 1 divided by a really, really big positive number, we'll get a really, really small positive number. So what happens is we approach 0 from the positive side. And you can see that that actually tracks up here. We can see that as x tends towards positive infinity, so that is positive infinity, we have y tending towards 0. This is being 0, y equals 0. And we have it approaching from the positive side here. And if we consider 0 tending towards, x tending towards 0 on the positive side, we have 1 divided by a really, really small positive number, and as a result, we start shooting up to infinity. Now, if we look at the negative side, we have 1 over x. We consider x tending towards negative infinity. Then we have y equals 1 over negative infinity. And so y is tending towards 1 divided by a really, really large negative number gives us a really, really small negative number. And we can see that this also is respected by the hyperbola, given that we have this bit here corresponding to here, and we are approaching 0 from the negative side. And now if we have our 1 divided by 0 approaching 0 from the negative side, that is from this side, we can see that 1 divided by a really, really small negative number will give us a really, really negative large number. And so as a result, as x tends towards 0 from the negative side, we have y approaching negative infinity. So this is something that I'll go over in a little bit more detail in the hyperbolas lesson, and the inverse proportion lesson more specifically is what it'll be called. But for now, I hope you have a bit of an intuitive grasp of how hyperbolas work. So I'll make a little bit of space and consider x to the 1/2. And this is known as the radical function or the square root function. So this first function that we dealt with here, this is the hyperbola. Now we'll have a look at the root or radical function. And so the root or radical function is written as y equals x to the 1/2. And from index laws, we know that that's equal to the square root of x. And so if we consider a graph, the easiest way to deal with a root function is to just plug in values of x. So we know that here, if we plug in a 1, we will have y equals 1. So at 1x, we have y equals 1. At 4, we have y equals 2. And so we end up going up this way, and so on and so forth. And at 0, we are still defined by anything negative. We can't have the square root of a negative number. And so as a result, we have something that looks kind of like this. Okay? And so here, as x tends towards positive infinity, we have the square root of positive infinity. So y also tends towards positive infinity, just at a rate slower than x. And as x tends towards negative infinity, we have the square root of a negative number, and so that doesn't exist. So we actually only start at 0 here, and we keep going. The reason why we don't have this is because the radical function here is only defined for positive values. If we're solving, for example, x squared equals 9, remember that we always write plus or minus square root of 9, which is plus or minus 3. Okay, so this radical function here is by definition positive, and that's why we need this positive and negative in front when we are looking at solving quadratic equations like this. That's just a side note. And so this is a root or radical function. This is relatively straightforward, I'm hoping, and it is something that we'll revisit a little bit more later on down the track, maybe in some of the supplementary content, or if it pops up again in the syllabus. Okay, but otherwise, let's move on to expanding and factorizing quadratic and cubic polynomials. The two syllabus dot points that we're going to be dealing with are 1.13 and 1.14. And what we're doing is we're trying to expand factors to obtain quadratic and cubic polynomials. And similarly, what we're doing is we are having a look at the Cartesian representation of cubics of different forms. And this will be heavily inspired, and I'll be drawing a lot from what we've kind of discussed in our quadratics session, because a lot of these have very similar properties. So, first of all, let's revisit quadratics, and let's say we have a function y equals x plus 3 and x plus 4. If we want to expand something like this, what we do is we multiply our x's, we multiply our x to the 4, 3 times x and 3 times 4, and as a result we end up with x squared plus 4x plus 3x plus 12, which is equal to x squared plus 7x plus 12. And as time goes on, you'll be able to go straight from here to here. Now, if we're looking at cubics, we have y equals maybe x plus 1, x plus 2, x plus 3. And we can see we have here 3 linear factors, 1, 2, and 3. And so we will have an x squared at some point. We'll have x times x times x. And that's by definition here. Remember also that given x plus 1 squared for x plus 1 cubed, we can use the binomial theorem to expand, and so we end up getting something like x cubed plus 3x squared plus 3x plus 1. And you can verify that that's the case using the binomial theorem. But in this case, we'll have to first expand one of these, that is, for example, this part here, and then multiply that by x plus 3. So let's do that. So, in these first two linear factors, we have x plus 1 multiplied by x plus 2. Okay? And so this, if we expand this, gives us x squared plus 3x plus 2. And then we still have to multiply that by x plus 3. And so if we use our similar, this was something that was always introduced to me as the crab clause method, you can multiply your x squared by the x, then your x squared by the 3, then your 3x by the x, 3x by the 3, 2 by the x, and then 2 by the 3. And so as a result, you accordingly get, oh, let's move that, x cubed plus 3x squared plus 3x squared plus 9x plus 2x plus 6. And you can pause the video to see where I get each of those. It's basically just using that crab clause method. And so if I write this out again, I get x cubed plus 6x squared plus 11x plus 6. Alright. We're not going to look at factorizing until a bit later. That's something that uses some techniques that might be a little bit too complex for now, but we'll introduce that later on. So, okay. Recognizing features. Okay, so now let's have a look at 1.2.4. And we have 3 different ways of writing a cubic here, and in fact they'll all be a little bit different. So we have our line, our cubic y equals x cubed first of all. And here our line y equals x cubed, we will have, the way that this looks is it will have something called a point of inflection at our point 0, 0. When x equals 0, y equals 0. When x equals 1, y equals 1. When x equals 2, y equals 8. So we're going to make a massive leap here. When x equals -1, y equals -1, because -1 cubed is -1. And -2 cubed is -8. And so as a result, what we end up getting is something like this. And this is the form of y equals x cubed. Here we have one stationary point. And remember in quadratics we always had turning points where there was a stationary point. Here, this is what we call a point of inflection. What a point of inflection is it's a concavity change. So if we were looking at quadratics and we have something like this, this is known as concave down because the concave component here is pointing downwards. This is concave up because the concave component is pointing upwards. And so here we can see if we sketch out the other part of this, we can see how we're switching from a concave down to a concave up. Okay? And more specifically than just a point of inflection, it is a horizontal point of inflection. We have vertical points of inflection that kind of look like this as well. And those would be, for example, here. And so if we look here, we can see we've switched from a concave down into a concave up. This will be a concept that becomes more familiar to you when you deal with a branch of maths called calculus. All right, so we've defined a horizontal point of inflection. Let's take a look at transformations or translations done to this horizontal point of inflection. If we have y equals a, x take b, all cubed plus c, this is kind of like your turning point form from the quadratic formula. You will have a point of inflection, and that point of inflection will have shifted from 0, 0 to the point b, comma, c. And so as a result, when we draw a graph again, like this, we will have our similar shape. Oh boy, that's not a great drawing. And that should be horizontal here. And So this has this isn't exactly horizontal, is it? No. Okay, so this is a horizontal point of inflection, and now this point here will be at the point B, comma, C. This is a vertical dilation scale factor similar to the A in our quadratic. So if we are looking at 2x cubed, for example, or 2x take b cubed plus c, what generally happens is everything gets stretched out in the vertical direction. So what was initially at x equals 1 is now at x equals 2. And what was initially at x equals 8 is now at x equals 16. So essentially what happens is we have something that goes much steeper down like this. Okay? And this is going to be something we formalize in the formal definition of what a function is. Okay, I'm just going to move these over a little bit so we can have a look at the root kind of form of a cubic. And so that's this form here, the root form. Okay, and so we have a y equals k x take a, x take b, and x take c. And so if we draw a Cartesian representation of that, this will look something like this, where these are our roots, similar to the root form of a quadratic. We have our points A, B, and C corresponding to A, B, and C. And we note as well that as x tends towards positive infinity, we're going to have y tending towards k times positive infinity. And so as a result here we can see that because as x tends towards infinity, y tends towards infinity, this must mean that k is positive. If k is negative, we end up having something that looks kind of more like this. Okay? Maybe I should draw that in a different color. I'll draw that in a dark blue. So if k is negative, we end up seeing something like this. Okay? And what k is, again, is it's a vertical dilation factor. And so if we're changing k, what generally happens is everything gets pulled out in the vertical direction, but we still always have the same intercepts. And so, sorry, A does have some effects on dilation, but it's different to k. This is more like a k value here, because it'll act as the coefficient of your x cubed. Oh, this kind of does act as your coefficient of your x cubed. Well, in the case of you expanding this, your k and your a will assume slightly different values and be distributed across slightly different values. I don't think there's too important of a distinction there, but they both have dilation effects, and that's something we'll revisit, and hopefully it becomes a bit clearer later on. Okay, so I've got that. And so we've had a look at what the effect of k is, if it's positive or negative. So if it's positive or negative, and we know our roots. Okay. So let's go from Cartesian representations of cubics to the equations and vice versa. Okay, so that's our next stage. So what we want to do is, for example here, first of all, this is probably the easier way of doing it if we've easily obtained it from the graph. So if we have a graph like this, and we can see that it looks like this, the first thing I know is that if I write it as y equals k, x take a, x take b, and x take c, I know that my k value here is going to be positive, because as x tends towards infinity, positive infinity that is, y tends towards positive infinity. Okay, so I've got this sort of trend happening. And as x tends towards negative infinity, we've got y also tending towards negative infinity. So that's a clear representation that k is going to be positive. Now the next things here are that this value is equal to -1, this is 1, and this is 3. These aren't the best exact. Yeah, this clearly isn't 1 and 1, but that's okay. We'll just leave it as it is. Maybe I'll just change this to a -2 actually. And let's say, for the sake of the argument, we also know that this point here, it's not the turning point. Maybe we should pop it somewhere here. Oh boy. Yeah, so I'll just put it here just so I can write 2. But this is not the turning point. We have 2, -3. And this information is enough to tell us what the equation of my graph is. I could similarly have a y-intercept here, and maybe that's, I don't know what that is, because I don't want it to conflict with this. Anyway, so now reading off this graph, we can easily factorize, we can find a factorized cubic. So we have this point here, we can have this point here, and we have this point here. Okay, and so as a result, we know that our form is going to be of the form y equals k multiplied by x plus 2, x minus 1, and x minus 3. And we also know that we have the point 2, -3. And the way that we can find k is by substituting these values into the equation. That is -3 equals k, 2 plus 2, 2 minus 1, and 2 minus 3. So we have -3 equals k times 4 times 1 times -1. We have -3 equals -4k, and so k equals 3/4. And so as a result, our final solution will be y equals 3/4, x plus 2, x minus 1, and x minus 3. And we can also find the y-intercept of this equation by expanding that out. And I can show you a bit of a quicker trick. We just kind of consider the constants here, and we do 3/4 times 2 times -1 times -3 will give us the y-intercept, and that in this case is going to be equal to 18/4, which is 4.5. Okay, so we know we have a y-intercept at 0, 4.5, and that's this point here. Okay, so we can also factorize cubics that are given to us in non-factorized form. So I'll just rub this out here and have a look at one such example. And to factorize expanded cubics, we use something called I think it's called the factor law. I'm not quite sure. Your textbook will mention something about it. But essentially what you do is, let's say you're given a function, a cubic function, and I write that as f of x, or I can write that as y. But in this case, I'm going to start adopting f of x equals x cubed plus 6x squared plus 11x plus 9. Hang on, let's see if that's a good example. -1. Okay, so let's take a look at this one. So x cubed plus 6x squared plus 11x plus 6. Now, the way that we can determine a factor of this cubic is by plugging in a value for x and seeing if it's equal to 0. And this actually, now I remember, is called the factor theorem. And so in order to determine a factor of f of x, what we do is we plug in some value. And so I know that this is just something I know, but this is something you would do by trial and error, is you would plug in random values for x and see if one of them equals 0. In this case, I know that -1 will equal 0. So f of -1 is equal to -1 cubed plus 6 times -1 squared plus 11 times -1 plus 6. That's equal to -1 plus 6, take 11 plus 6, which is equal to 0. And so, as a result, because -1 is a solution, that must mean that x plus 1 is a factor. And so, I know that x plus 1 is a factor. Now, to factorize further, I can have two different methods. I can, first, factorize by inspection, and I'll walk you through how to do this. Or I can also factorize using algebraic long division. And some questions might ask you to use a specific technique over the other. So both of these are important to know. So I'll label this I, and I'll label this method II. So in the case of I, what we do is we know that f of x can be written as a linear factor multiplied by a quadratic factor. So f of x can be written as x plus 1 multiplied by ax squared plus bx plus c, and that's equal to x cubed plus 6x squared plus 11x plus 6. And so if we consider and try to expand this out to get to the same, we can see first of all that a is going to be 1 because we know our coefficient of x cubed is 1. So x times ax squared will be equal to ax cubed, and so a is equal to 1. Now we consider our x squared coefficients, and we think about how can we form those x squared coefficients. We can form those x squared coefficients by multiplying ax squared times 1, and also by multiplying x by bx. Okay, so we know that bx squared plus ax squared is going to be equal to 6x squared, just equating those. We also know that a equals 1, so that means b plus 1 x squared equals 6x squared, and so b plus 1 equals 6, which implies that b equals 5. And finally, we know if we're looking at our last value here, we know that to form the constant, we must be multiplying each of the constants in each of the factors. And so we have our 1 and we have our c, and as a result, c must be equal to 6. And so we have f of x equals x plus 1 multiplied by x squared plus 5x plus 6, which if we factorize that quadratic is going to be equal to x plus 1 multiplied by x plus 2 multiplied by x plus 3. Okay? And so that's the final factorized form of that quadratic. All right, method 2, algebraic long division. This is something that it takes some students a bit of time to wrap their heads around. So I'll try to go through this relatively slowly. And this is something I would recommend you have a look at in your textbook as well. So this is method 2, algebraic long division. What we do here is we have our x plus 1 as our factor, and we're dividing x cubed plus 6x squared plus 11x plus 6 by x plus 1. And so the first thing I want to do, just with normal long division, is we look at our highest value here, and we try to find how many times this value goes into that value. In this case, x plus 1 goes into x cubed plus 6x squared plus 11x plus 6, x squared times. And so it goes in x squared times, and for those x squared times, we end up getting x cubed plus x squared. And we subtract those to get 5x squared plus 11x plus 6. Now we need to figure out how many times x plus 1 goes into 5x squared plus 11x plus 6. And to do that, we consider our highest value here. And we can see that x here goes into 5x squared 5x times. And so as a result, we have 5x multiplied by x plus 1, 5x squared plus 5x. And so we end up with 6x plus 6. And this goes up here, plus 5x. And we know that x plus 1 goes into 6x plus 6 6 times. And so we have a remainder of 0, which we would expect. And we have divided it to get x squared plus 5x plus 6. And so now we can write our cubic as f of x equals x plus 1 multiplied by x squared plus 5x plus 6. Some students might find this method easier, others find factorizing by inspection easier, but it's important that you know both. And unless it asks you to use a specific technique, use the one that is easiest for you. And so we know from previously that this factorizes to x plus 1, x plus 3, x plus 2, x plus 3, sorry. Alright, if we wanted to graph that now, we know first of all that our k value, that is the coefficient of all of these individual factors, is positive, and we know the roots. As a matter of fact, we also know where the y-intercept is. And so here we can see that we have a root at -3, -2, and -1. We also know we have a y-intercept, which is the multiplication of each of these constants, 1 times 2 times 3, and so that is at the point 6 here. We also know that our k value is positive, so our cubic will look like this rather than something like this. And so as a result, we end up with something like this as our final graph. And so we've indicated all the key points. This looks like a cubic-ish. Your cubic will hopefully look better than mine. So that's 1 mark for shape. Then you get 1 mark individually for each of these x-intercepts. And then you get a mark for your y-intercept. And you can apply similar principles to quartics as well in terms of factorizing by inspection, but they get a lot more complex, and generally this sort of factorization expansion sort of thing is restricted to cubics. You can also solve cubic equations using your class pad. You can graph cubic equations using your class pad, and that's something I'll leave up for you to have a go at. But other than that, that's everything from this lesson. We went over the features of graphs of y equals x to the n. We looked at n equals -1 and n equals 1/2. We looked at the shape and behavior as x tends towards positive and negative infinity. We defined what a polynomial was. We looked at what the coefficients and degrees are defined as. We were able to expand factors to find quadratic and cubic polynomials. We had a look at different types of writing the cubics and what they looked like on a Cartesian plane. We also factorized cubic polynomials using inspection and algebraic long division as 2 different techniques. Okay, cool. That's all of the video today. Remember to comment if you have any questions or if I've missed anything within this topic, and make sure you subscribe so you don't miss any new videos.